Hi, my name's Andy Karam, and in this presentation I'm going to talk about X-ray safety. What we're going to talk about is first the sorts of locations where X-ray generating devices are used. We're also going to talk about how X-rays are produced, a little bit about how the machinery works, and a little bit about the physics behind X-ray production, but not to worry, there won't be any equations to go along with the physics. After that, I'll discuss, especially in a medical setting, how some of the X-ray machine parameters can affect your radiation dose and the dose that the patients are receiving. And finally, we'll talk a little bit about X-ray safety, or about overall radiation safety in facilities that do use X-ray generating equipment. I should also say that radiation producing equipment is treated differently in the regulations from radioactive materials. If you have a device, it's something that can be turned on or off, and the radiation does not come out when the device is off. These are typically registered with the state as devices. Radioactive materials can't be turned off. A cobalt-60 source will always be radioactive. Radioactive materials are licensed by the state, and they're generally controlled much more stringently. What I'm going to be talking about in this talk are the X-ray generating devices, not the materials themselves. There are a lot of different types of facilities that use X-rays. The most obvious are hospitals. X-ray machines, fluoroscopy units, CT scanners all generate X-rays for medical treatment. What's not as obvious are some of the industrial uses for X-rays. Electron microscopes, SEMs and TEMs, or scanning electron and transmission electron microscopes, also generate X-rays, and in fact, in most states, they need to be treated as X-ray generating equipment. X-ray diffractometers are used in material science research, and they can generate very high doses of X-rays in the beam. Industrial uses also include things like non-destructive testing, basically X-raying welds or X-raying products to look for cracks or hidden defects. These machines also require some basic level of radiation safety or X-ray safety, and these devices are going to be registered with the state. One of the more common industrial uses for X-rays is for sterilization. High-energy X-rays are often used to sterilize surgical products and food supplies, and more recently they've been used to sterilize the mail as well. It's important to point out that unlike radioactive materials, such as radioactive sources, radiation-generating devices are usually registered with the state as opposed to licensed by the state. This means that the controls are not quite as stringent on the devices as compared with the radioactive materials. The difference between the two of them is that radioactive materials are always radioactive, whereas radiation-generating devices can be turned off or turned back on again, which makes them inherently somewhat safer. What we need to talk about next is how X-rays are generated, and it gets into a little bit of physics, but if we understand how X-rays are generated, it helps us to understand a little bit better how we can protect ourselves against them. It all starts with heating a filament, just like the filament in a light bulb, to high temperatures, which causes electrons to effectively boil off of the filament. These electrons are accelerated to fairly high energies, and they're slammed into a metal target, usually tungsten, sometimes copper. When the electrons hit this target, the X-rays are emitted. It's almost like sparks coming off when you strike two pieces of metal together or a couple pieces of quartz. The electrons hit the target, the X-rays are given off, and then those are sent towards the patient or towards whatever it is that's going to be X-rayed. When the X-rays are emitted, they have a wide range of energies. The highest energy that they can have is the energy that the electrons have. You cannot have X-rays that are more energetic than the electrons, but they can have energies all the way down to zero. This is important from a radiation safety standpoint. Radiation dose comes from depositing energy within your body. When the X-rays are low energy, they can be absorbed by your body but not pass through it. So if you have a lot of low energy X-rays, you can actually have a fairly high radiation dose, even in medical devices, and that radiation dose really does not contribute anything. This is one of the reasons why what we want to do is to try to emphasize, or we want to try to make the X-rays as high energy as possible while still being able to get the information out of them that we need. There are some machine settings that are common to any X-ray machine. These are the things that help to control the radiation dose from the X-rays. One of these is the kilovolts potential, which you'll see abbreviated as kVp. The kVp is a measure of the electrical current or the electrical potential difference that the electrons are accelerated through. A higher kVp means that the electrons hit the target harder, which means that they give off higher energy X-rays. So increasing the kVp increases the energy of the X-rays. This may sound counterintuitive, but higher energy X-rays actually give less radiation dose because they're more likely to pass through your body as opposed to depositing energy in your body. So if you want to reduce your radiation dose somewhat, you can actually increase the kVp and your dose will go down. Filtration is something else that we do. Remember what I said earlier, that X-rays are given off with energies going from 0 all the way up to the maximum energy that they can have, basically the number of electron volts that the electrons pick up. The lowest energy X-rays don't do anything, so why let them intersect your body at all? What we can do is to put a chunk of aluminum in front of the X-ray tube, and that aluminum will filter out the low energy X-rays, and it will only allow the X-rays through that will actually contribute something useful. So by increasing the filtration, we make the X-ray beam a little bit harder, and that results in less dose, or it reduces the radiation dose to the person who's near the X-ray machine or the patient who's being irradiated. The last factor that really has a bearing on X-ray dose are the milliamp seconds, or MAS. MAS is just a measure of how many electrons are hitting the target, and since each electron can produce an X-ray, the lower the MAS, the fewer the electrons hit the target, and the lower the dose is going to be. So that one actually makes sense, even at first thought. So again, increase the kVp, increase the filtration, decrease the MAS. All of these things will result in a lower radiation dose for you or for whoever else is exposed to the radiation. With any X-ray source, whether it's a hospital machine or an industrial machine, there are three basic principles of radiation safety: time, distance, and shielding. You should try to minimize the amount of time that you're exposed to the radiation, be out of the room when the radiation device is on, or at least minimize the amount of time that the device is on when you're in the same room. If you minimize the amount of time that you're exposed to the radiation, your dose is going to be lower. Distance is the second one. Radiation dose drops off as the square of the distance. If you double your distance, even just taking one step back from a device, your dose is going to go down by a factor of 4. So you should stay at the greatest distance possible from the source of radiation while still being able to do your job. Obviously, if you're a nurse, you may have to be at the patient's bedside or right next to the operating room table, and in that case, you just don't have a choice. But if possible, even then, you should try working maybe near the patient's head or near the patient's feet if you can still do your job, if, say, their chest is being X-rayed. So maximize your distance from the source of radiation, and your dose will drop fairly dramatically. And the last is shielding. If you're in a room with an X-ray machine, you should wear your lead apron. The lead apron will